That's nice. We're going to finish up 6.5 today. It doesn't look like there's a ton left, but the last problem on 6.5 is going to take us a decent chunk of time. Please have a calculator out today. You're going to need a calculator. And yeah, then we'll jump into 6.6. I don't know how far we'll get into 6.6. I want to leave a smidge of time to potentially talk about the homework, and especially number 3, because it is a little sneaky. Okay. So I've talked to a couple students already about number 3. So the answer might be slowly but surely trickling its way out into the crowd. But I'll talk about it too, just to make sure that everyone's kind of has a decent chance at it. All right, let me recap where we were at yesterday. Yesterday, we started looking at these graphs, which are known as phase change graphs, okay, and how to interpret them and how to do some calculations with them. The big thing to remember is that we have basically 2 different types of areas on this graph. We've got these parts where there's an incline or a change in temperature, because Y is our temperature, okay? And then we have these plateaus where temp is constant, but energy is still being added, because along our x-axis here, the label is energy added, okay? So throughout this process, we are constantly adding energy. Sometimes when we add that energy, or that heat, I should really say, we are changing temperature. Other times when we add that heat or energy, temperature is constant, okay? If you look at this graph, we can kind of break it down into like 5 specific regions. We have this initial incline, the first plateau, the second incline, the second plateau, and the third incline. Each spot is unique. Before we hit that first plateau, this is nothing but pure solid, okay? In this instance, we're talking about ice, this first graph, or sorry, water, right? Both of the graphs I gave you yesterday were for water. So in this first part right here, we have nothing but solid ice, pure solid ice. It started off at -40. We heated it up until we hit 0. At 0 degrees Celsius, we've reached the melting point. At 0, it starts to melt. And now I've gone from my pure solid to some mixture of solid and liquid between the phases during the phase change, to nothing but pure liquid at that point right there. At that point, now, once I have pure liquid, I can heat that liquid up until we hit its boiling point. And at this spot right here, all the way over to the end of that plateau, we are undergoing a phase change again, from liquid to gas. After that point, we have 100% pure gas, and then we can continue to heat that up and change its temperature after that fact. So 5 unique spots, right? Pure solid, phase change, in this case melting, because we're going from left to right across this table. Pure liquid, phase change, going from liquid to gas, pure gas. Okay? We're going to calculate all that stuff for the very last problem on this table, or on this page. And it's not too bad. It really isn't. We just got to make sure we're using the right equation. We had 2 equations at our disposal. The first one we're very familiar with, hopefully by now. We've been using it all week. Q equals mc delta T. The big giveaway here is the delta T. If we're not changing temperature, we can't use that. Make sense? Okay. So this will be for the 3 spots. Oops. Where we have temperature changes, pure solid, pure liquid, pure gas. We'll use that equation to calculate the energy added during those periods of time. The other equation is Q equals m delta H. Delta H is enthalpy. It's the fancy word for heat or energy. Okay? We have an enthalpy of fusion, which is talking about either melting or freezing. Okay, the phase change that goes between solid and liquid can go either direction, right? Sometimes we go from solid to liquid, melting. Sometimes we go from liquid to solid, freezing. But fusion is talking about that phase change, either direction of it. We also have an enthalpy of vaporization. That's talking about the other phase change, going from liquid to gas or gas to liquid, boiling, condensing. Okay? So we have two values for that. One for the lower plateau, one for the upper plateau. And we'll use the one that's appropriate for what we need to know, or what we're trying to figure out. Okay? We did one of these problems yesterday at the end. I've got one more here before we hit the big one at the very bottom. But let's try number 4. Using the molar enthalpy of vaporization for water, how much energy in kilojoules is needed to boil 3.64 moles of water? The molar enthalpy of vaporization we calculated yesterday. We did a lot of unit conversion yesterday. That's very common with these types of problems. Okay? Can you convert from calories to joules? Yes, I know that there are 4.184 joules in a calorie. Can I convert from joules to kilojoules? Yes, there are 1,000 joules in a kilojoule. Can I convert from grams to moles? Sure, just depends upon what substance I'm using. If it's water, my molar mass is 18.016. That's grams per mole. I can convert between those two things, right? So there are conversions that need to happen fairly often in these types of problems. But let's use this for number 4. And let's solve for the total amount of energy. How much energy in kilojoules is needed to boil 3.64 moles of water? We are undergoing a phase change. We're kind of, sort of, using this. Kind of. I say kind of because M is mass. Is that mass? It's not. It's moles. But we're going to use the delta H in terms of energy per mole. Okay? So you can think about it like we're using this, or you can just kind of do it factor label style and realize that when I take the moles multiplied by the energy of vaporization, the enthalpy of vaporization, that is kilojoules per mole, the moles cancels out and I'm just left with kilojoules. Right? Maybe that's a better way of thinking about it. Maybe I'm confusing you if I write that up there. I don't know. Okay. 3.64 moles multiplied by the enthalpy of vaporization is 40.7 kilojoules per mole. Right? How many total kilojoules of energy are required to boil our 3.64 moles of water? Huh? 148. Thank you. 148. Okay. So this is pretty easy, obviously. We're just multiplying two numbers together. If you know how many moles of substance you have, you can use the molar enthalpy. Now, the molar enthalpy is just the fancy way of saying how much energy per 1 mole, right? Well, it takes this much energy per 1 mole. When I multiply these together, the moles cancel, I get my energy. At the tail end of yesterday's class, we did the opposite. We used mass and the enthalpy of fusion in this instance, but this was in a calorie per gram basis. All that matters is that your grams and your moles match up, right? I don't want to use grams if my value of enthalpy is per mole, because then nothing's canceling out and I'm getting something weird that doesn't make any sense. I don't want to use moles if my value of enthalpy is per gram, because then it doesn't cancel out and it doesn't make any sense. So you're just trying to match the units, right? If I have mass, let me pick the enthalpy that is per mass or per gram. If I have moles, let me pick the enthalpy that is per mole to make sure I'm doing it correctly. That kind of makes sense? It's just a label thing, really, I guess. All right. Here's the big one. How much energy is required to heat 45.2 grams of negative 40 degrees Celsius ice up to 140 degrees Celsius steam? Hint, this requires 5 steps. We have 5 equations that need to happen to get this total. For each step, we will add them all up to get our total. Okay? So let's go back to the graph for just a second. 45.2 grams, okay. We are right here. And I want to end up way up here at 140. I guess, yeah, right here. Okay? And I want to know how much energy does it take to get from there to there if we're heating up 45.2 grams of H2O. Each region gets a separate equation. We will have 5 values of Q, 5 values of heat. 1 for how much heat it takes to heat up the solid ice. 2 for how much heat it takes to melt it. 3 for how much heat it takes to heat up the water. 4 for how much energy it takes to boil the water. And 5 for how much energy it takes to heat up the steam. Okay? So let me get you started. Q1 equals something. Okay? What equation do we want to use for the first chunk of this graph? We are heating up solid, pure solid ice. We want to use Q equals MC delta T. Why? Because the temperature is changing. Yes. Yes, let's pick that one. Okay. So my Q1, I'm going to use MC delta T. And what's my mass? 45.2 grams. What's my specific heat capacity of ice? Yeah, I gave that to you. It's different than liquid water. I warned you about that yesterday. Now, I could have been mean and not given that to you, but I'm feeling nice. There it is. Okay? 0.504 calories per gram times degrees Celsius. And then my delta T is final minus initial. For my first portion of the graph, what's my final temp? Yeah, it does, the very first graph. Sort of. I mean, you can use it as a reference. The hard part is that first graph, like the energy added on the x-axis, doesn't matter because that was for 1 gram. This is for 45 grams. So we have to calculate the energy added, but the shape of the graph is perfect in terms of where it starts and where it ends. Sorry, so what was our final temp? 0, right? Because once we hit 0, then we enter that second part. We enter the phase change, and we need a separate equation. So for the heating up of just the pure solid, we end at 0 degrees Celsius as our final temp. What was our initial temp? Negative 40. So final minus the initial, right? Make sure you get your signs correct over there. We are subtracting a negative value, which in turn will turn it positive, right? And Q1 should equal how many calories? Say it again. 911, you said? Okay. Is there a second on that? Cool. Sweet. That's the first chunk. I'll do the second chunk with you, even though I think you can do it. Q2. Is for the phase change. What equation do we use during a phase change? M delta H. Okay, now delta H of what? Fusion. Careful, yeah, those are fancy words, but fusion is the freezing melting one. Vaporization is the boiling condensing one. So we're going to use delta H of fusion. I'll go delta H FUS. I set this up. What's my mass? It is, and it's never going to change, by the way. 45.2 grams. What's the delta H of fusion, the enthalpy of fusion? 80. Yeah, we had done that previously, right? We have 80 calories per gram. And that's it. What's Q2 equal? How much energy does it take to melt this stuff? $3,616. Thank you. Sorry, I just had to hear better. So on and so forth. There are 3 more steps. Q3 is heating up the liquid water. Q4 is boiling the liquid water into gas. And Q5 is heating up the steam. Do the last 3 chunks, and then to get the total, we add Q1 plus Q2 plus Q3 plus Q4 plus Q5. I'll give you a little chunk of time here. Shouldn't take you too long.
No, I'm just.
Okay, I got my setup for the other three. What's Q3 equal? When we're heating up the water from 0 degrees Celsius up to 100 degrees Celsius, how much energy does that take? Okay. Q4? 24,408. And last but not least, Q5. Anyone have a mistake or a dispute in any of those? Take that as a no. Now, we have the heat required to heat up the ice from -40 to 0. The heat required to melt the ice from pure solid to pure liquid. The heat required to heat up the water from 0 to 100. The heat required to boil the water from pure liquid to pure gas, and the heat required to heat up the pure gas. That's everything. We went from -40 to +140 degrees Celsius, and we included 2 phase changes along the way. How much total energy did it take? Well, Q total, we'll switch colors one more time just for fun. Okay, do you need to write this out? No, but I'll write it out anyway. Q total equals Q1 plus Q2 plus Q3 plus Q4. Okay, what's our Q total? 30 what, huh? 4,000. Thank you. Sorry. Pretty easy. Just kind of tedious, and make sure you use the right equation at the right time, and don't use the wrong specific heat capacities, right? That'll screw you up. You have to make sure you pick the right specific heat capacity when you use the delta MC delta T. It's different for different phases. But that's it. Any questions on 6.5?
How do you add energy to calories? How would you do it in real life?
Well, calories is just a quantity, right? So it's not like you can specifically just add this much, I guess, if that's what you're asking. It's just that we can calculate how much it would have required. So, you know, you could do this if we took like a 45.2 gram, you know, ice cube at -40 degrees Celsius, if we had a way of monitoring its temperature, and we just put that over a flame, right, and did the whole thing. And it was in a sealed container and all that good stuff, and we could calculate its temp all along the way until it turned into 140 degrees steam. Like, it'd be hard to control adding specifically this quantity, but we could calculate like what it took, so to speak. That's kind of what we're doing. It's not like, yeah, there's not an instrument that's like, I want you to add 34,000 calories and that's it. And then it zaps it with a laser for, maybe there is, I don't know.
So like, how would you even get close if you don't even know? Like, if you can't measure it and do it, how would you know if you're?
Because what you can do one of two things, right? You can either just like aimlessly add a bunch of energy and see where it goes, or you can use a calorimeter. So a calorimeter or a bomb calorimeter is a sealed, completely closed off, enclosed container, where if you know the quantity of energy that you're adding, like through a chemical reaction, or if you're burning some sort of fuel that you know how much energy is released per molecule that gets burned, or per gram that gets burned, you can calculate how much you've actually like added, so to speak. So for example, there's a lab in Science 9, I think it is. Were you 9, 10? Okay. There is a lab in Science 9 or Science 10, I forget which one, where they use alcohol burners and they calculate like how many calories of energy like are burned off of that alcohol burner. No? Maybe they got rid of it. Either way, I mean, so there's there's ways of knowing like how much energy you get released from a combustion reaction. And then in theory, you can like take the mass beforehand and the mass afterward to see how much you burn. And then, yeah. Were you a 9-10er? Nelson did that with you guys? Yeah, I never know where they all go with the other curriculum stuff, but all right. So we're good on 6.5. Let me jump into 6.6. I'm going to try not to take up too much more of the hour because, like I said, I do want to talk about question number 3 on the homework before. No, it won't take the rest of the time.
I don't know. It's pretty complicated.
Would you like me to talk about it right now? Okay, I can do that. Either way, I mean, I'm jumping into 6.6, but let me talk about number 3 on your homework because it's a little tricky. What I said to somebody the other day was that this is more of an algebra problem than it is a chemistry problem. It's basically like, I don't know, algebra using chemistry as a context. So in question 3, it says you've got 50 grams of 280 Kelvin water. Am I right?
30 grams.
Sorry,
30 grams.
30 grams of 280 Kelvin water, and you're mixing it with 50 grams of 330 Kelvin water. And the question is what's the final temp after they're done and they reach thermal equilibrium? So we know you have to use this equation. By the way, okay, this is number 3, homework, unit 6, topic 1. Just making sure anyone that's watching the video, if they're just fast forwarding and doing other things, maybe they can see what I'm talking about now. So we have hot water and cold water, and we know we're going to have to use this equation, right? We have to. That's the only equation I've given you to that point in time. The hard part is I can use this equation for the hot water, I can use this equation for the cold water, but I can't solve for Q in either situation, can I? Because what do I know? I know M for both. I have a mass for both. I know C for both. That's good. I don't know Q, and I don't know the final temperature. So whether I'm trying to use this for the hot water or whether I'm trying to use this for the cold water, I don't have complete information. We have to get sneaky. Okay? However much energy is lost by the hot water is exactly the same quantity of energy that is gained by the cold water. In other words, the Q lost by the hot should equal the Q gained by the cold. We can set these two equations equal to one another. But we have to be a little careful. Because again, for the hot water, this will be negative. For the cold water, this will be positive, right? Because the energy is either lost or gained. Hot water loses energy, cold water gains energy. The same quantity, they'll lose or gain the same amount, but the one that loses is a negative, the one that gains is a positive. So what you have to do, okay, is you set them equal to each other. And I have to flip the sign of the hot one so that they both are positive values. Because inherently, the Q of hot is going to be negative, right? So I'm going to take and flip the sign of this because I know that negative Q of the hot will equal positive Q of the cold, which in turn will mean that negative MC delta T of the hot will equal positive MC delta T of the cold. Okay? So let's put parentheses around those. Now, that's all well and good. Correct. You have initial temperatures for both, right? The final temperature for both? Yes, and it's the same. So TF in both of these is the same. Now the hard part here is maybe the algebra. You got to make sure your algebra doesn't fall apart. So you'll end up with mass times C times TF minus TI, mass times C times TF minus TI. The only thing you won't know on either side is TF. You're going to have to combine those terms eventually and solve for it. Careful with your algebra. Okay, that's the setup. That's all I'm going to give you. Well, I'm not going to do it for you.
I need to
that's
fix
good.
that.
Yeah, I'm kind of.
I'll like solve it, but.
What do you
I
mean?
agree. You just do all the work for us, and
No.
then give us the answer, and then we'll know.
No, it was just implied. I mean, a little bit. That should be plenty. Yeah, because now it's algebra. Now it's not chemistry anymore. I gave you the chemistry. Yes, you do.
The change in temperature thing.
Yeah.
Change in temp equals TF minus TI, right?
Yeah.
You know TI for both. You don't know TF for either,
Correct.
but it's the same number. You have an X on this side. Well, yeah, it's an unknown, right? So you can treat it as like, you know that X minus something you know.
Wait a minute.
You know that X minus something you know.
Yeah, that made sense.
Did it?
Yeah.
Okay, now it's algebra.
Wait a minute, now I forgot for a second. Oh, I remember again.
You remember your order of operations. You got to be a little careful. All right. Put that away for right now. You were excited about me telling you to put your homework away?
No.
Oh.
Almost got it, I thought.
Let's jump into 6.6. We'll see how far we get. I got 20 minutes here. I might be able to get a decent ways in. This isn't too bad. This will be easier than I think what we just did. The conceptual stuff of what I just taught you, like the whole unit conversion stuff from yesterday, I know was kind of dense and miserable. This is a little more straightforward. This is kind of more factor label-y today in terms of the math. And I don't think it'll be too bad. So today we're going to talk about the enthalpy of a reaction. In other words, the delta H from a chemical reaction. Okay? So calculate the heat absorbed or released by a system undergoing a chemical reaction in relationship to the amount of reacting substance in moles and the molar enthalpy of the reaction. That sounds fancy. The objectives from AP are always fancy, but I'll break it down into more simple terms. Okay. All right. I left those two equations up there for a reason, because I'm just going to use them to explain something. Chemical reactions have a certain amount of energy associated with them. Over the course of a chemical reaction, you will either gain or lose energy. Often this is signified or shown by the change in enthalpy. Okay. Enthalpy, for our purposes, is what? What have I said that enthalpy is, time and time again? Heat. And I'm not changing that. Okay, that's my one-word definition. Do you see the word enthalpy? You think heat. Now, let me explain why I can say that. This is an equation not in your formula packet, but that is true. the change in energy of a system is equal to the heat plus the work of that system. Okay? So delta E equals heat plus work. Now, this equation is also true. This is not a part of your packet either. But the enthalpy of a system is equal to the change in energy plus the pressure times the change in volume. Now, this term right here in chemistry is known as work. This is going to get a little confusing. Hang with me. Okay? The enthalpy equals the change in energy plus the work. 9 times out of 10, sorry, more than that, 19 times out of 20, maybe more than that too. 94 out of 95 times, just to make it obscure, we aren't going to do any, this sounds bad, work, okay, in chem. We are not in a closed system where pressure and volume changes. So long story short, this term just kind of goes away. And the change in enthalpy equals the change in energy. And the change in energy equals the heat plus the work. But we did no work. So what does the change in energy equal? The heat. And if the change in energy equals heat, and the enthalpy equals the change in energy, therefore, enthalpy equals heat. Am I making sense? Okay, so again, is enthalpy heat? In actuality, no. But for what we're up to, it is, because we're not going to do any work in any of these problems. That makes sense. So when you see the word enthalpy, please think heat for the 8th time this week that I've looked at it. You all right there, Jim?
Yeah.
You get your homework problem?
Yeah.
Congratulations. When the total enthalpy change of a chemical reaction is known, we can use this value stoichiometrically with the coefficients to determine how much energy is gained or released for a reaction. Whole bunch of problems. That's all this sheet is from here on out. Okay? How much heat is released when 1 mole of water is produced? Here's my chemical reaction. For this chemical reaction, the change in enthalpy is negative 572 kilojoules. Negative, what does that mean? If the enthalpy is negative, what is that trying to tell me? We lost heat. What's the term for that? That was you, right?
Yeah. Exothermic.
Yes, it's exothermic. Sorry, when somebody whispers behind a mask, I can't quite tell who's
I know,
done it.
I'm gonna say this is wrong.
It's not wrong, it's right.
I know, but it was.
But you're good. You're usually good. Take a shot, you're good. So negative, that's exothermic. This reaction is releasing heat, aka energy, aka enthalpy. Okay? So how much heat is released if I make a mole? I'm making 1 mole of product. How much total heat is produced? This is just factor label. I'm going to start with what I know. I produced 1 mole of water. And then I can set up a ratio. In this balanced reaction up above, this releases 572 kilojoules of energy. How many moles of water did I produce up above? 2. So, for every 2 moles of water that I produce, I release 572 kilojoules of energy. We can set it up as a factor. The enthalpy of a chemical reaction can be used just like any other ratio of any other chemical in that setup. So my ratio between energy and water is that for every 2 moles of water, I get this much energy. And then I just plug it in, which you shouldn't even need a calculator for. Negative what? 286 you said? Sounds about right. Easy. Try another one. How much heat is released when 4.03 grams of hydrogen react with excess oxygen? Why do I have to say that this is an excess? Why do I have to say that one of my reactants is excess? Yeah, what I'm trying to say by doing that, right, is that the oxygen is irrelevant. You got as much as you could ever want. If I gave you a specific quantity, now I've turned it into a limiting reactant problem. And yes, that does happen on this sheet before we're done. Okay? But let's set this up. How much heat is released when I have 4.03 grams of hydrogen reacting? 4.03 grams of hydrogen. I eventually want to get to energy, right? But I can't do grams versus energy, can I? Got to go to moles first. That makes sense, right? These are molar ratios. So I can only make a comparison between my reactant and my energy if I'm in moles. Because I know for every 2 moles of hydrogen that I burn, I get that much released. Well, how many moles of hydrogen is this? I don't know. Let me figure that out, right? Next factor, grams of hydrogen. What's the molar mass of H2? Okay. Now we're at moles, and now we can use our ratio. For every 2 moles of hydrogen that are burned, we get negative 572 kilojoules of energy. Can't even remember my number. 572. So how much total energy is released when 4.03 grams of hydrogen are reacted? What do we get? Works for me. 571.7, you said? I'll just keep it 3 sig figs. Try C. Go for it. Don't try D. D gets a little funky. But please try C. I'll give you a little minute here, and then I'll jump back in and show the answer. We'll do D together. For you? I've said I would love to, but it's not exactly a school board approval situation. Wouldn't get anywhere. There'd be no kids okay.
I would, sorry.
No, how do you?
I would.
That would be,
We have one group.
I would probably-
and you two get along the whole time?
No.
No, this happens every year. My juniors in AP chemistry every year in the spring. Ross, how come you don't teach any more chemistry?
See, you have all the juniors.
Yeah.
But then literally, like, you take chemistry 3 years at Wasabas High School
No.
and no other science. That's not a well-rounded education.
It's better than anything
You're speaking my language.
else. Like,
I couldn't agree more.
Yeah.
I couldn't agree more.
I'm taking bio.
Yeah, same.
This is like,
I also said this class. Wow, just relentless.
I'm sorry.
I mean, you're wrong. You're wrong.
I'm not sure.
I'm not biased. You're just wrong.
Oh.
No, I'm very biased, obviously. Okay, whatever. No, that's fine. That's perfectly fine. This is for everybody. I get that. Some people like it. Some people don't. I don't think any less.
Jeez, everyone is killing me today.
What happened?
She said everyone does.
No one likes this?
no.
Oh.
Save that one real quick.
He saved it, yeah.
No, I mean, but okay, time out for a second, quick second, right? Like, when you talk about chemistry out to like anyone in the public, like your parents or your aunts and uncles or whoever in your family, what's like the first reaction when you say chemistry? Yeah, exactly. No, but 9 out of 10 people are like, ugh, I did so bad in that in high school. I did so bad in that in college. Oh, I hated that class. My professor sucked. Like, that's like the general, 5-comment collection of chemistry thoughts.
There's like TikToks of people like crying because of that.
Yeah.
Haven't got there yet.
You haven't made one of yourself crying yet, is that what you're saying?
Oh, it hasn't made me cry yet.
Oh, okay. That's good. I don't think I will. I don't generally have that effect on people. 186 grams of oxygen. Ooh, I'm gonna trip. We're gonna convert that into grams, into moles. What's the molar mass of O2? Careful. Yep, it's diatomic.
I did write down.
1 mole to 572. How many total kilojoules do we get released? Say that again? I didn't hear you. Is
I have 1,600.
that right?
Negative.
I got a negative 3,320. That's what I
Yeah.
Did you,
Oh, I
you 2 moles of oxygen?
divided by 2.
Yeah, I almost did that. I was like, wait a minute.
Yep, make sure you look at the right ratio, right?
Yeah.
1 to, yep. All right, cool. How much time do I got? No. All right. We'll deal with the Hindenburg tomorrow. That's the last problem here. It's going to combine a couple things from things we've done earlier this year with this new stuff. Folks online, thanks for joining me. I appreciate it. Have a lovely day. Homework topic 1 is due tonight. With my help on number 3, hopefully you're in good shape.
It's that, I
Yeah.
still give that to you.
Yeah, I did too.
But it's
It doesn't make sense, but yeah, that's exactly what I was saying.